Great. Well, it's fantastic to be here. This is ringing some old bells for me that you may not recognize, which is back in the 1990s. This is before Akamai and content distribution networks. At Inktomi, we built the first overlay network, which essentially was a network of proxies, a lot like Istio, that had a remote control plane, but it was proprietary, and it certainly was not as ambitious as the things you're talking about today. But it has some similarities. We had like forward proxy caches in front of Yahoo. We had, reverse proxy caches are called. We had forward proxy caches at AOL, and they were connected, and you did all the management at kind of the HTTP layer 7 controls, not at the underlying network controls. That was actually quite a fun set of things to work on. It all got killed when the internet bubble burst, and telcos took like a 3-year hiatus on spending money. And so those things just kind of died in the spot, although Akamai certainly did continue to do very well and recovered. So a lot of these problems actually are very similar to some of the things we worked on in the 90s, although again, the scope and ambition, and there was no mobile in that case, is totally raised up. And a very fun set of projects. So today I'm going to talk about Kubernetes, which is a project I helped start at Google in 2013. It's done pretty well. This is not directly related to the things that you're working on, although I think it's a building block, and it's certainly something that many customers are using. We see it already experimented in about 70% of enterprises. It's one of the obvious approaches for multi-cloud applications because it's open source and relatively portable. And so it has a fast rise. So I'm going to talk about what it is, and I'll talk a little bit about Istio, though less than what's already covered. But this is really understand Kubernetes as a part of your context. So I would say we're in this middle of a transition to what I kind of call the new cloud. And sometimes people call it cloud native. What I mean really is that we are no longer thinking about the cloud as machines and disks. We're thinking about the cloud as services and APIs with essentially highly available services taken for granted and expected on many fronts, not just the telco front anymore. And that when you're working in this space, you assume essentially infinite resources. Right? There's a very big difference between designing something where if I want to expand, I always can. If I want to do a new deployment, I can do new deployment next to my first deployment. I don't have to do it on top of my first deployment, which actually greatly simplifies availability and evolution. So this is kind of the direction. This is also how Google has worked for I've been there about 7.5 years, well before I got there, at least a decade. And in particular, the way Google runs its infrastructure is actually not with VMs generally. It's essentially with containers on bare metal. And the reason for that is not because we're opposed to VMs. It's because, like Inktomi, Google was started in the 90s. In the 90s, VMs hadn't yet been reincarnated. Right? Disco and VMware are kind of 98 technology. That's the same year that Google was founded. So Google actually built all of its infrastructure with essentially no use of VMs, which means you're running applications directly on bare metal, which in turn means that you need some way to package and distribute things that are not virtual machine images. And you also, turns out, you need a way to make sure you can run many applications on the same machine without them interfering too much. So containers are our basis for that. I'll talk about what I mean by containers in a minute. But literally everything runs on a container. In fact, if you use Kubernetes on Google Cloud, you have your own container in Kubernetes. It's running on a VM. That VM is running inside a container on Google's cloud. Right, so we actually have multiple levels of turtles here going all the way down. When I say everything is containers, I really mean everything, and that's why you get this 4 billion launches per week. Every day, everything that's relaunched is a set of containers. That is the unit of deployment. So one complication here is what are containers? There's actually 2 different definitions that we've merged, and that causes confusion. So I'm going to talk about both. The popular one is Docker. Docker is a packaging format. You can think of it as a fancy tar file. It's very clever. It's a good design. And really, it says, I want to put my software and all of its dependencies in some kind of hermetically sealed thing, and I'll call that thing a container. And that way, when I deploy my container on my laptop, it works. When I deploy it in the cloud, it works also because now the things it needs are inside the container. And so that ability to have your production stuff match your testing environment is very handy. Another kind of containers, set of containers, the kind that, oh, I see I'm off a whole slide. Wow, that's funny. The other kind of containers are Linux containers, which is what Google was using 10 years ago, which are really the resource boundary for running an application. So it's not about packaging, it's about resource isolation, so that when I have two applications running on the same node, I can split the cores, I can split the memory, I can split the network bandwidth, and actually contain each of them. So for example, if I have a rogue web server, I don't want it to be able to take all the network bandwidth and mess up all the other applications on the same physical machine. That's what resource containers give. So when we do containers now on Kubernetes, it's actually both these things together. It's a Docker-like container, or literally Docker, running inside a Linux process that has resource isolation turned on. Right? How this affects the platform is we kind of have something you would think of as a PaaS, app engine. You can write, or serverless functions. You have machines at the bottom. This actually fits in the middle, meaning that it's a general purpose infrastructure based on processes and APIs, not based on machines. So what's nice about being in this middle layer, this is the Goldilocks layer, right, is that it's as flexible nearly as VMs. VMs can do some things that Kubernetes can't do, but not, I think, things that are particularly important. But it's productive like higher level languages are productive, like services are productive. So you get higher velocity, but you still get great generality. So it really is intended to be a new cloud platform that is fully general. Easy to use and flexible. So in this model, what do you think about? You tend to think about composition of services. You tend to think about, I want to do load balancing. I have to name my services. I have to figure out where my state is. I'd like monitoring and logging to be just built into the platform. That's very similar, by the way, to what Istio is going to provide for ONF kinds of things. Upgrading is an important thing. I want to be able to upgrade a service, and I'll talk about all these. What you don't think about, actually, is things like, do I need to patch my OS? Do my packages have conflict, kind of like DLL hell? Do I worry about exactly what size machine I have? It turns out not much, because we can be very flexible. I actually don't want to worry about what language I'm running in. In fact, I want applications to be multi-language and have that just work. And a subtle one is I don't want to worry about port conflicts, because ports are this weird thing where they're known to applications like port 80 for HTTP, but they're also a machine resource. And so if I have 10 web servers on a machine, which one gets port 80? Right, I'll come back to that problem. But we're not going to have to worry about that in Kubernetes, and I'll show you why. And all this really is about velocity and evolution, that I should be able to deploy a new version of my service relatively independently of the rest of what is going on, and it should just work, right? That's really the goal of these microservices. And you say, how micro is a microservice? What I really mean is it's the size of a team. It could be a big team, could be a small team, but it's the unit of deployment, it's the unit of teamness, of cooperation. And because of that, typically a given microservice will be in one language, but it can mix with other services written in other languages. What is a service? Well, it's really just a long-lived abstract name. Right? What we most care about is that the name you use to invoke a service is highly available. The actual implementation of that service may go through many iterations and may change all the time, but that churn has to be hidden from the users of the service. And that's both if the user is people or the user is other services. Now, I'm going to skip the next set of slides in time because I want to get to some different stuff, but I would say this is kind of like service-oriented architecture, except that was kind of big services, and this is actually lots and lots of small services. And this works better because the services match the size of teams. And I'll show you a little bit of structure on that. So if you were to look at your code, it has all kinds of stuff that is mixed together. You have code that you wrote, code that's open source and you've imported, stuff that's secret, stuff that's open. And we don't really want all these things just mixed together in a monolithic application. What we want is some substructure so that I can say, oh, the application boundary is finer grained than that, and I can mix things at different boundaries. So I'll show you how we get substructure. Let's start first with what containers do. Containers, as I mentioned, are really just, in the Docker sense, are about package dependencies. So I can have on one machine 2 different versions of glibc or 2 different versions of Python. That works okay because that's no longer a machine decision, it's a container decision. So that's one kind of structure. It turns out we want another kind of structure because of these mixing of codes and teams, which is a pod. This is a Kubernetes change to the space, which is a pod is essentially co-located containers which share volumes, and in particular, because they're co-located, you can use localhost networking to connect the different containers in a pod. This also is how we solve the port problem. A pod is the unit of IP address allocation. So each pod has its own IP address. So if I have 100 pods on a machine, which is not unusual, that machine will have 100 IP addresses, and every pod gets to have port 80. Right? This is a problem, solves lots of problems, but I think the important part of is that DNS works. Right? What we did internally at Google, which didn't work very well, is we would actually dynamically allocate IP addresses. So if I had 100 pods on a machine, it would not have 100 different IP addresses, and we'd have to dynamically pick ports for things like web servers. Then we'd have to tell everybody what the port number was. But you can't use DNS to do that, at least not traditional DNS, because it doesn't include the port number. So this model actually is an improvement of what Google does internally by quite a bit. So we have lots of IP addresses. We'll give an IP address to every pod. Now you get the full port space. You don't have to negotiate ports, and DNS just works. So why would you want multiple containers in one pod? Well, there's lots of reasons. I'll switch to the one I wanted to show. I don't have a great one. This is similar. This is the adapter pattern. So again, the 2 containers are coming from 2 different teams. So I have kind of the main application. That's from one team. But then I also have a logging team. And the logging team writes the logging code. And by the way, the Istio or Envoy team writes the Envoy code. So Envoy actually works the same way in Kubernetes. It's a sidecar. So sidecar is basically just another container that goes in your pod that comes from a different team so that you can guarantee that those 2 teams can work together in an easy way, right? So they're co-located, but they're actually deployed differently. They can use localhost networking to talk to each other, and that's what gives both teams high velocity. So that's the reason for the pod and the sidecar. And again, that's exactly how Istio works. It's a Envoy sidecar that goes in the same pod as your application. Now it's doing all of your service proxying. Another kind of abstraction in Kubernetes is a service. Now, I'm going to kind of differentiate between simple services and complicated services. Kubernetes, I would say, by itself gives you simple services, by which I mean it's a load-balanced thing. Istio turns simple services into complicated services where you can do things like policies and access control and billing and telemetry, right? All the other things you would like on a set of services. And I'll come back to that in a little bit. But just Kubernetes itself, what it gives you is essentially a highly available name, which I told you is the most important part, and a way to vary the implementation over time. So in particular, the way to think about it is there's a notion of a load balancer built into Kubernetes, right? Every time you define a service in Kubernetes, that implies there's a load balancer there. It's typically, with base Kubernetes, a relatively simple load balancer. It could be like layer 4, for example, ITP-based load balancing. Later, when you use Istio, you have layer 7 load balancing instead. And the way it works is each service has a bunch of pods that are defined to be identical. So I might have 10 pods implementing a service. If I want to have more capacity, I add more pods. And they can be on the same machines or different machines. But the pods are the unit of auto-scaling. And they are defined to be exactly the same in the sense that they are rubber stamped from the same specifications. If I add a pod, it starts from a template. If I shoot a pod, we just kill it. And if I restart it, it restarts from the same template. And across those transitions, there is no state kept. So you have to do state management separate from that. And this gives you basically an easy way. This is the core abstraction for a highly available service, right? If you want to do an upgrade, which I'll show you in a minute, you can change the pods without changing the service IP, and people calling the service don't know that you're changing the pods, right? That's the level of indirection. So I want to walk through that example. It's pretty interesting. It's a little complicated. So the goal here is evolving a service from version 1.2 to version 1.3. Now, there's some things on this picture I haven't introduced, so let me introduce them. The first thing is the blue box, light blue box, which is a replication controller. And what that does is it basically has a goal. And the way Kubernetes works in general is you state the intent of what you want. You declare your intended state. And the system tries to make that true. That's called reconciliation. So what happens in the replication controller is when you have a service, or in general, any collection of replicated pods, replication controller has a target number. So here, for version 1.2, the target number is 4. So it says, I want a replicated set of pods with 4 pods. There are 4 pods, so everything is good. Right, so what's implicit in this is there's a kind of API here which says the way I'm going to add a pod is not by calling the add pod function, which would be imperative. It's by changing the target number to, say, 4 to 5, such that that indirectly causes the creation of a new pod. So I'll come back to that in a minute. You'll see it through the example. Now, there's many different kinds of pods, so the replication controller needs to know which pods is it supposed to be watching. And the way that's done is with labels. So a label is the thing that's in orange, that's v1.2. And so the actual semantics of a replication controller are take a label, v1.2, find all the pods of that label. There's 4 of them that have that label. Does that match the target number? So that's the actual control loop. Query for pods with labels, count the number, see if it matches the target. If not, delete or add. Right? That is literally what a replication, and you can go look at the code, but it's all open source. It's very short. I also said there's a front end, because every Kubernetes service has a load balancer. The front end also uses labels. So in particular, how does the front end know which pods to send traffic to? And the answer is all the pods that have the same label. So the load balancer is looking for the label front end. It does a query, finds all the pods that are labeled front end, and it will send traffic to those pods. Again, declarative, not imperative. So when we do an upgrade, what we're going to do is create a new replica pool for the new pods that implement the new version. And it says, I want 1 pod of the new version. Well, that's not the current state. The current state is 0. So in fact, it's going to create a pod. It has the new pink label. And that new pod showed up with the label front end. So what does that mean? That's going to get detected by the front end doing its loop of looking for pods with the label front end, and it will start sending it traffic. So in fact, we've changed 1 number. We've already caused 2 actions. We've caused the pod to be created. We've caused the front end to send it traffic. Right? Now the declared state matches. Right? The front end declaration matches what it wants. Both pod specs match what they want. Both replication controller specs. Now we're mixing traffic across these 2 versions. We can go a little farther and say, well, now I'm going to start taking away the old pods. So I'll change the replica count to 3 in bright yellow, like that. And I will, you can guess what that's going to do. It's going to cause a pod to disappear. And the front end will obviously stop sending it traffic. We can go add a new pod on the new version. Change it to 2, right? Creates a pod, gets discovered, gets traffic, right? And you can see how this is going to work. We're just going to keep changing these numbers, deleting all the old pods, creating the new pods. But all we're doing is playing with these 2 numbers. All the rest follows from those declarative changes. Right, that is the essence of reconciliation, and it's a very robust thing. Because what happens, for example, if someone deletes a pod accidentally? A new one will get created in the same way. It's no different than changing the number from 4 to 5. If the number's at 4, and in reality drops to 3, it will put it back up to 4. So that's what makes it robust. It works. It's an eventually consistent declarative system. Eventually, we'll add the last pod here, and we'll delete the last pod of the old thing. And now we're completely on the new version. This is actually how service upgrade works in Kubernetes. But I like this example because it actually shows you labels, replicated pods, and declarative spec and reconciliation. By the way, Istio uses the same declarative spec model. So you declare what your policies are, and it will then go push those policies out to all your proxies. Right? And it's very, very similar based on the same reasoning. Now, one other example on this front, if I suppose that I had a buggy pod and I wanted to figure out why it was buggy. Well, I don't have a picture for this, but if I just take the front end label off of a pod, the pod still exists, it just stops getting traffic. Right? So the way you debug this is you take the label off, you can then either SSH into that pod or use other tools to actually understand why did that pod get stuck and debug it. Right? So it's there for debugging, it's just not getting any traffic. And in fact, if you fix it, you can put the label back on and it'll start getting traffic again. Right? Just to give you some insight into how these mechanisms get used in practice. So the next step, now that we have all of our things on a new version, and by the way, because, again, there's a service IP, the IP address is the same. You could have live load on this. If you notice, we always had at least 4 pods. So we never had a loss of capacity during this transition, right? We always had at least 4 pods, and we had 4 or 5 in all cases. When we, so moving on, I want to talk about, I've given you basic services, but I really want higher level services that offer more infrastructure for services. And Google runs, I don't know the number now, but when I last looked a few years ago, it was like 10,000 services all the time, which seems like a crazy number. I can't name 10,000, like Gmail's a service. Now, in practice, of course, there's many services because there's a whole bunch of things going on underneath the covers. But there's tens of thousands of services. It might even be 50,000 by now. And so you can't manage them one at a time. You need tools to manage collections of services. And that's really what service meshes are about. And by the way, even smaller things like, Spotify here has 1,000 services, right? So they're not, what you think of as being one service is itself thousands of services. So what we want to do really is a few things. We would like to be able to deploy service updates independently. And of course, that needs versioning. We'd also like to have really uniform and easy support for services. So for example, how does telemetry get collected from these services, right? How many calls were they? What's the latency? Well, we don't want every team to worry about that. We want one team to worry about telemetry, and they do the telemetry for all the teams, right? So really, we want the telemetry and any kind of horizontal property of services to be done horizontally and not individually for each surface. And finally, a goal is it'd be nice if, when I wanted to change the policy, I don't want to have to redeploy the service just for that reason. So if I can take policies out of the source code of services, then I can say developers work on the functionality of their services and operators work on the policies, and they actually don't have to argue about it, right? If you have launches blocked because you have operational issues that you have to argue about, that slows down velocity. So it'd be nice if I could say, let's put all the operational issues outside the source code of the service somewhere else, and that somewhere else is going to be a proxy. So that's really what Istio's for. I hadn't actually thought about using it for a global multi-edge network until I saw the earlier talk, but it makes perfect sense to me. It's very similar, actually, it's very similar to what we did with Traffic Server in the 90s in some ways. And it is open and it works quite well. So in particular, we have this Envoy, which is an extensible L7 proxy. It does a lot of things. Obviously, it does better load balancing. It does the data collection for telemetry, so monitoring and logging, things like that. And again, you can do it for all the services the same way. So you say, I want my services to track 99th percentile tail latency. That you put in this layer, and now all services have that. Right? And in fact, you don't even have to redeploy the services. You start getting that property immediately. Because deploying a new policy to Istio is essentially instantaneous. It has nothing to do with redeploying the service. Security is an important one. It turns out that when I have service chaining, I'd really like to know if service A is calling service B, that it really is service A and not some rogue service. So one of the things built into Istio is that it authenticates not users, but actually services. So service-to-service communication ends up being authenticated in both directions and encrypted. And again, applications don't do anything to cause this. It's all done in the proxies. Then all kinds of other things. Actually, previous talk had a better list, but DDoS support and quota, billing, rate limiting, circuit breaking, all that stuff goes in these horizontal layers. And service mesh is just say, let's make all the services have the same proxy control infrastructure. That's really, Istio is really two things. It's the actual proxy, which is, although based on Envoy, in some sense, there's also people working on an Nginx version. There may be other versions. The part that makes a difference is that the way you program those proxies is from this uniform control plane. And that's where you get consistency of policy. Right? So those two together are what actually give you the power. So a few minutes left. I'll just wrap up the kind of a few philosophical bits. So one of them is for Kubernetes and now Istio and things like Knative, which is for serverless, we decided to make the core pieces of these open. And that's because this is too big a transition for any one company to do. Right? Trying to get modern cloud to be cloud native with services and APIs is something Google, as big as it is, cannot do by itself. And if we did do it by ourselves, we wouldn't do as good a job. Right? The community input is super valuable, and Kubernetes is one of the largest projects ever in the history of open source in terms of the number of contributors and the rate of commits. It's many, many updates per day. TensorFlow is a similar thing, which I won't talk about, but same idea. Let's try to get a framework that's open and can be widely used and widely contributed to. Istio, we just talked about. GRPC, I didn't talk about, but actually it's what we use when we don't want to have JSON everywhere. You might notice in this room that JSON is pretty darn slow. gRPC is a much faster RPC protocol. It's what we use internally, essentially. We use a version of it. And if you're worried about the performance of HTTP and JSON in all your services, you should very seriously look at gRPC. That's what it's for. For example, there's ways in gRPC you can do client-side load balancing where you can get some of the benefits of Istio without having to have a proxy on your data path at all. Right? We do that internally for bigger services. So gRPC should be on your minds as something that if you're worried about performance of this architecture, that's what you should go look at. And there are reasons to be worried about having proxies everywhere. In fact, there was one data path in Google where I think we had, for a while, not advocating this, 13 software proxies on the path. Right? That's just because it was convenient for deployment at that time to have that. It's much lower now. But I'll give you an example. For example, if I have one layer of Istio for cloud control of services, like I want to make sure we're doing billing in a safe way, that has to be an Istio proxy controlled by Google, because its billing is security sensitive. But our users may be running Kubernetes, and they may have their own Istio for implementing their policies. So in fact, just there, we're going to have two different layers of proxies, one that's customer controlled and one that's infrastructure controlled. The customers won't see the infrastructure controlled one, but it's there, and it wouldn't surprise me if for things like global IP addresses, there's actually a third proxy somewhere else, which is about making sure you get to the right region. So there will be layers of these proxies regardless, and there'll be lots and lots of software. So getting these things to be quick is important, and it's been good progress on that front. Now, last thing I would say, one of the big advantages of the approach is it does work on-prem, and you can actually mix services on-prem and in the cloud, and all the things I heard this morning about multi-edge and multi-cloud, this fits very well with both Kubernetes and Istio. Because they're open, you get consistent behavior because the source code is the same at these different locations. And as far as I can tell, the only way to get consistent behavior in a fast-moving space is to use the same source code. Right? You can't do it the traditional way of like internet specifications because the space moves too quickly. Right? But if you do it by source code, you get consistency by definition, mostly. Still some things to worry about. And that's why this is, I think, moving quite quickly. All right, so I'll just stop here, see how much time we have for questions. But that's a kind of quick overview of Kubernetes and how it relates.
Yes, I think we are going to have at least some questions, but I want to start myself with one. So, Eric, I mean, you've been involved in Kubernetes from the beginning and all of that. So, can you say a little bit more about the journey and the amount of investment? I mean, you said how popular Kubernetes is, what number of contributors, commits, and all of that. But can you briefly say where it came from, what kind of investment Google made first, and then before it put it out, and then what continued investment Google is making? Sure. So that will be very helpful.
So in general, Kubernetes you can think of, and even Istio and GRPC, as rewritten versions of what Google was doing internally in the previous 10 years. So we had this thing that's the Borg scheduler. It worked on Linux containers. It was the thing that was deploying containers. We had things, one of them is called One Platform, which is basically a service infrastructure for horizontals. That's very Istio-like, but was, again, proprietary. And so Istio and Kubernetes are really open source rewrites of things we've been doing for a long time, but we rewrote them for two reasons. One is the first systems have big flaws, like the port one I mentioned, where we have to do dynamic ports internally. That's a big mess. And those systems are also, like Borg is huge. It's a 10-year-old behemoth that we would love actually to get out from under. And we will move to Kubernetes internally at some point as well. But it just has a lot of baggage that would not make it an appropriate thing to even try to open source. So Kubernetes is a clean reimplementation of its ideas, modernized for Docker, modernized for idea of cloud resources and IP addresses. And so the first 2 years of Kubernetes was pretty much Google trying to sort all this stuff out. And I think I did the first public talk on Kubernetes in that DockerCon in 2014. Then we started to get real contributions from other players. Now Google is still the largest contributor, but we're less than 50%. And that's good, right? I don't want us to be more than 50%. I want us to be 30% or 20%, because that means other people are meaningfully engaged, and that has happened.
So during those 2 years that when you were trying to rewrite and get Kubernetes out in the open source, how large was the team that was doing it? Is it half a dozen people, 20 people, 50 people?
It grew over time. The first version was 3 to 5, depending on when you ask. And then it became, when we decided to do it, which is a big decision I was involved in, I think we got that up to around 20 or so for a while, maybe 30. And now it's hundreds. And Istio is a separate collection of a large amount, and GRPC is a separate collection of a large amount. But it is, I would say, one of the biggest bets Google is going to make in general in the cloud space is on this kind of modern cloud with services, APIs, Kubernetes, Istio, because we believe that is the most productive way to use infrastructure.
Okay, very good. Thank you. Okay, I guess we are running out of time, but still I can't let Eric go that easily, and he's such an important person. So any other question from the audience?
Yeah, I have a specific question to the use case that you use Kubernetes for the running upgrades. So I'm looking at it from the perspective of the typical ISSU that we use for ancient devices, and usually it's based on redundancy. So you're doing the upgrades based on redundancy. So you have a redundancy set of pods that you're changing it one at a time in order to move to the new version. The first question actually I wanted to know is the load balancer at one point of time was talking to two different labels, 1.2
yes.
and 1.3. And I wonder how does this work, because usually the load balancer is only talking to one set of labels, or basically one version, so that because of the consistency. But I don't know how you manage those. This is number one.
We actually, in general, try to make it such that when you're doing an upgrade of a service, the vast majority of the time, those two have the same API, or the new API is backward compatible, right? So that gives the two teams autonomy. We do have cases where we change the API, and then you can't use the simpler version I just said. But that should be rare. I think people make those versions different way more often than they need to. Like, for example, Borg has, I think, 1,500 RPCs now. That's because we only add RPCs, we never delete any. Now, that's an extreme case. I actually think that has problems. We took it too far, right? But because we only added RPCs, we could always forward rotate services and users.
Right, and the other, maybe you got away with this, but the other one is how would we manage if I only have one pod that I wanted to upgrade to another pod at the same time without interrupting services?
I think by definition that's not possible unless you could stage the pod.
I know, exactly. So you always depend on redundancy to doing this rolling.
But the cloud model is you have a place to run the new one because you have excess resources that are elastic.
I see.
All right, so I think you should actually try to get some elastic resources even at the edge. You don't need many. Right? You need space for one extra pod, and that can be 10% of your load if you're clever. Doesn't have to be, double the size.
Thank you.
Okay, any other questions? Any other questions? Sorry.
Hello, yeah, this is Arun here. I have a question about.
No, okay, here.
Sorry, there you go.
Yeah, I have a question about this GRPC. So, P4 runtime and then GNMI and GNOI, they are taking over almost all the RPC mechanism, I believe. So, still, you think that GRPC has a future, and you have a plan to move towards the GNMI and GNOI?
I do think gRPC has a future. Whether it'll be adopted more broadly, I don't know. But I do feel like when we've had customers try it, they've always liked it. And a lot of that is it's just faster, but it is a bit more structured too. The problem is it's not, you can take APIs where you can generate a gRPC version or a JSON version, and we do that. They're not exactly compatible, so it's better if you generate two versions than try to convert from one to the other. But there are also people that have written kind of mediators, which are essentially higher level proxies that actually do impedance mismatch for those two protocols. I don't love that either, but I do feel like for new things, you should at least look at gRPC because it is a very good protocol and better than JSON for lots of use cases.
Okay.
Just one clarification on the last question. So P4 runtime, GNMI, and GNOI are all services that are built using gRPC. So we're actually using gRPC under the covers, and we're just defining different services in all of those cases.
Well, that's great to hear. That's what I would have recommended had I known you were doing that.
Okay. Okay. Last two questions, and then I think we should stop.
Great.
Hi. My question is really, what are you doing now? What are your top one or two challenges, and where do you think this is, that you need to overcome to go to the next level?
It's a good question. I would say, and I by definition can't give you a perfectly honest answer to that question, but I'll give you a directionally honest answer. So I would say there's too many things right now that are still alpha and beta, including parts of Istio. And so first thing is just get all the stuff to be, Kubernetes is now pretty verbose. Like if you try GKE on Google Cloud, that is a remarkably good service. I think 11 of the 18 top retailers used GKE in production for Black Friday and had 0 outages. So it's actually production ready. But I would say newer things like how you do policy management, how you do identity stuff, how you do namespaces, which basically how do I have different domains of control in the same service, which you need if you say I want this stuff for credit card processing and I want this stuff for mobile banking and I need to keep the two separate. So there's a lot of obvious next things that just need to be stabilized. Beyond that, I think the next step is really making it easier to do true hybrid and multi-cloud operation. We have customers doing that now, but I would say it's still early days for that. And beyond that, it's if I'm a next generation software author, I feel like this is the platform you should target, right? Don't target a VM image, target containers on an open, broadly used platform, because now the services you write on top of Kubernetes with these relatively small restrictions, they're going to run on multiple clouds, they're going to run on-prem, and you actually have a much easier deal as a software developer. Right now, if you want to run stuff that runs on Azure, Amazon, Google, and VMware, you have to write it kind of 3 or 4 times, right? And this would solve that problem.
Thank you.
Okay, last question then. Any? Okay, maybe not. So let's stop.
All right.
So
Thank you so
again,
much.
thanks so much, Eric. Really appreciate it.